So here for iron 2, it's pretty easy because just have the 2 valence electrons here. That leaves these inner shell, which is the argon and 3d6. Iron 3, though, can form as well, and if something can strong enough to plug off that 3d6 electron. So first to go are the 2 4s electrons and then the 3d. Iron 3, though, is a moderately strong oxidizer, so it's not so happy being in the +3, so it can oxidize things. In fact, you saw iron 3 before as an oxidizer. Do you recall where you saw iron 3 behaving as an oxidizer? The thermite reaction. The thermite reaction is rust, which is iron 3, and aluminum. Hydrogen can go both ways. It can lose or it can gain. All right. The next thing we're going to look at, atomic radius. This first sentence pretty much sums it up here. Unfortunately, atomic radius is hard to define. Why is it hard to define? It's hard to define because atomic radius depends on what you use to probe the radius with, And so if you're trying to probe the size of the atom, so let's say you have a probe that's smaller than the atom, which there aren't, but if you have some kind of probe, and you try to push it into the atom, are you going to hit a hard surface, like an eggshell, like a wall or a barrier? No, it's all empty space, and you just have this electron cloud that's around it. And so all the probes, the probe size, use electric fields to determine it. And so the closer you get to the nucleus, the more positive charge you build up. And so what they're looking at is they're looking at the negative charge density of the electron cloud and the positive charge density of the nucleus. And then they have a probe that kind of measures, the electric field. But when you measure, how do you define, the surface of an atom? That's not so easy to do. Further complicating this is that when atoms bond, if they bond tightly, they can squeeze into each other's electron clouds more, right? If they bond loosely, then they don't squeeze. And so the exact same atom in a strong bond is going to have a smaller radius than the exact same atom in a weak bond. And so what we see is we see variation in atomic radii, depending on what it's bonded to and what kind of field we're encountering. And therefore, we have different radii that we deal with. So this is in the table here. So let's look at 3 examples of sodium. The first radius is the covalent radius. If we had the Na2 molecule, you can make this molecule. Normally sodium doesn't make molecules, sodium makes metal crystals, and those are metallic bonds. But if you isolate this is going to be unstable in the gaseous phase, then you get 2 sodium atoms bond together. This is what we call the covalent radius, here. The electrons should be shared equally. The covalent radius, when we look at it, is going to be 157 picometers. So we measure the radius by taking the distance between the nuclei. Now, there's no solid boundary like this red. This red is just a 95% probability, or 90%. When you bond these two, they actually penetrate into each other here, and therefore shorten the radius. So the radius is just half this distance. Now, the Heisenberg uncertainty principle, this uncertainty and in position and uncertainty at energy, largely impacts the electron, but as far as the nucleus goes, do we have significant uncertainty in the position of the nucleus? And it turns out no. You know, the position of the nucleus can be pinpointed pretty easily. It's just electrons are difficult to pinpoint. Electrons being a lot less massive. All right, below that we have this one, which is the metallic radius, 186. And so the radius went from 157 to 186 in the metal crystal. And then we have the ionic radius, which is 99 picometers. And so we see a lot of variation. Yeah. Well, obviously we shouldn't compare the metal with the ion because the ion is totally different. And so let's take a look at the radii first. And then see slow. Well, that being said, you know, well, what did they use for sodium? Did they use 156 or did they use the other one? And so if you take a look at this number for sodium, you know, the radii here, just for, not for the ion, you know, the sodium ion they used 99 here, but for the atom here they used 186. Forgot what it was. But what you see here is this. If you see something like oxygen, oxygen is 73 picometers as far as the radius goes. 73 picometers, that's the average. Because what you're going to see is, you're going to see a variation in this. Now, how wide is the spread, you know? And so if we have a whole bunch of average radii, we're missing something. Do you know how wide the spread is? And how much data that average is based on? Is that average based on one piece of data or thousands of pieces of data? And so the one important thing missing from this is what? If we're given an average, we would like to know at least the what?
Sample size?
The sample size, yes. The sample size, for sure. But the sample size doesn't tell you, you know, the same sample size from a, you know, a skilled, experienced chemist versus a beginner is going to be different, right? Even though they both take 3 samples, you'd expect a tighter spread, better precision from somebody who's had more practice. And so sample size doesn't do it all. We also need to know what? The precision, but how do we measure the precision? How do chemists measure precision? Well, they just look at it and see, oh, that's good precision, that's bad precision. No, they put a number on it. What's that number? They might put the standard deviation or the, well, one thing that incorporates both, you know, sample size. That is, the fewer the samples, the wider the spread. The more the samples, the narrower the spread. That's called the T factor. You know, the T factor varies. If you take, you know, 2 samples, you have a T factor of 12.5. 3 samples, it drops down, I think in the 4s, right? Etc. The T factor and the standard deviation. What takes into consideration both the T factor and the standard deviation? The 95% confidence limit. And so we're missing that from these averages, so we don't know how wide the spread is. you know, how narrow the range of radii are. And so we're just going to use this as is, you know. This is going to assume, well, the atomic radius of oxygen is 73, but, you know, plus or minus how much? I don't know, you know, because it might not be 73, as we'll see right now. Let me back up. Actually, I don't know where that's all right. As we want to see right now. So there's going to be a variation in the size of the oxygen, depending if it's bonded to hydrogen, if it's bonded to phosphorus, if it's bonded to carbon, the size is going to be slightly different. The spread, we aren't going to worry about it, but you have to keep it in the back of your mind that there's uncertainty in that size, right? There's going to be some variation in that size. Well, okay, now we're okay with that. We're just going to use the average. And so when we use the average, Are you going to have to know numbers?
Yeah.
You should know some numbers. Well, like how big is a hydrogen atom? A hydrogen atom is about 100 picometers. 100 picometers is 1 angstrom. And so atoms, this is what I wanted you to know. Atoms are about 1 angstrom in diameter to about, actually we'll figure that out. You're not going to have to memorize specific numbers, but what do you think the biggest atom, what's the biggest atom that you see here? Cesium. Cesium is the biggest. Atomic radius is close to 300. 300 as for the radius means 600 for the diameter. And so the diameter of cesium is about 600 picometers, which is about 6 angstroms. I don't know when it was, maybe the first week or the first couple of weeks. Actually, when we talked about chapter 2, and we were talking about the size of the atom, you know, how big atoms are. And then I said, at that time, I think I said atoms range in size from about 1 angstrom to about 5 to 6 angstroms in diameter. And so that's where I got it. I got the numbers from this table. You know, atoms are going to range from 1 angstrom. What's the smallest atom that you see? The smallest atom's not on here. You know? Let's be down here. About. This is missing. Okay, let's take a look at these patterns, though. You know what these lines represent? This is a period or a row in the periodic table. So when we go from lithium to fluorine, take a look at what happens to size. So lithium, we go lithium, and then beryllium smaller, boron, carbon, nitrogen, oxygen, fluorine. Do you see what's happening to size here? Neon would be even smaller. And the same thing, the size decreases going across from left to right. The size decreases. And then as we go down a period, so this is second period, third period, fourth period, the size increases. Mark the page. 374. And so we see it here. Basically, those graphs are just plotting the radius versus the atomic number. And so as we go across, you know, lithium, beryllium gets smaller. Look at, they progressively get smaller. And then as we go down, they jump up in size, but the same pattern holds going across. Going across, sodium's the biggest, chlorine's the smallest. Potassium's the biggest, bromine's the smallest. And then as we go down, it jumps up. Lithium to sodium, potassium, rubidium, they just keep getting bigger. down a column. The size of the gold ones for the neutral atoms. And that's what we're going to focus on, the neutral atoms. And so why are we observing this particular pattern? And there are some exceptions here. Are there? Not really. It looks pretty good. And so the first question is, why does size decrease this way? Because it's counterintuitive. The size should be increasing because we're adding more electrons. But the size is decreasing. So why is the size decreasing going across? So let's talk about that. Just pick this. Let's pick this, the first, second, third. Let's pick the third. Actually, that's not the third, is that? Yeah, this is. Let's pick the third period here. Let's take a look at this one. And so what's the difference between sodium and magnesium? Well, you know, first let's look at how many protons does sodium have. Sodium has 11 protons, right, in the nucleus. Magnesium has 12 protons in the nucleus. How many electrons do they have? Well, sodium has the neon core, which is 10 electrons. And so in the neon core, we have 10 electrons. Magnesium has the same thing. In the neon core, it has 10 electrons. Well, right off, we see that the orbitals in magnesium are smaller because the core orbitals are all smaller. Why are the core orbitals all smaller in magnesium than in sodium? Yeah, they're drawn to the protons, and this has extra proton. This is more positive charge. More positive charge is going to pull the electrons closer. So for one thing, these core orbitals are smaller. Oops. Than sodium. Okay, now the next thing is this. In sodium, we have one valence electron. And what that valence electron sees is called Z effective. Now, core electrons are great shielders. And so what essentially happens is this. The Z effective that we see here, that is, we have 11 positive charges, but there's 10 electrons blocking it from the core. And so Z effective is close to 1. Plus 1. In other words, for the core electrons, they block out positive charges quite effectively. So out of the 11 positive charges, 10 of them will be blocked out by the core, leaving essentially this electron to see 1, a net 1 plus charge. Does that make sense? Okay. Now, as we go over here, we have 2 electrons in the valence. And so this will be the 3s orbital. In the 3s orbital, we got 2 electrons. 10 of these are going to be effective at shielding, but this electron is the same shell electron, what we call the same shell electron. Same shell electrons are poor shielders, are not effective. I mean, not terribly effective shielders. They will shield some of the charge because a same shell electron can come in here and block the charge, but essentially this electron is going to see plus 2, right? Closer to plus 2 than plus 1. And so in other words here, this is very crude. Z effective is going to plus 2. Not very accurate. It's closer to 1 point something. You know? But anyway, the point is that, you know, we have we're adding, as we go across the period. As we go across the period, we're adding a proton and a same shell electron. So each step we take going across, we add a proton and a same shell electron. And so increasing Z, increasing same shell electron means Z effective increases as we go across the periodic table. And so as we go across the periodic table, the size gets smaller because Z effective increases progressively. And so when we get to aluminum, even though this is in the p orbitals, we're just going to call it the same shell because it's the 3s and the 3p. And so now we have 13 protons. 10 of those are going to be shielded by core, and the remaining will be shielded by the same shell, which isn't as effective. And so Z effective, crudely goes up to +3, +4, +5. And the higher Z effective is going to pull in all the electrons closer. When we go from sodium to potassium, we're adding a shell. And so going down, we add a shell. Z effective is pretty much the same here. Because sodium has 11 protons and 10 electrons. Potassium has 19 protons and 18 core electrons. And so Z effective here is about the same. It's about +1, but the size is going to be much bigger because we have a whole nother shell of electrons in there. And so the size should increase as we go down. Size should decrease as we go across. Okay, where's the biggest atom? Where do you see? Smallest atom will be hydrogen or helium. Let me test you. The smallest atom will be hydrogen or helium. Helium's the smallest atom. Because Z's just increased to 2, but we have one more electron, but that electron is the same shell electron. It's not a good shielder. So helium's the smallest, around 100 picometers. What's the biggest? Francium. Francium's radioactive, so it's often left out. So we'll talk cesium. Well, here it's rubidium. We saw cesium earlier. Rubidium is about 500 picometers. So atoms range from 100 to about 500 or 600 picometers. Cesium's big. Cesium's closer to 600. Okay. What happens when you make an ion? So, for example, sodium ion. Take a look. Sodium metal, sodium ion. When we go to sodium ion, what's going to happen? Well, when we go to sodium ion, it loses the valence electrons. When we lose the valence electron, then we have 11 protons pulling in 10 electrons. What's going to happen to the size? It's going to get even smaller. And so when we make an ion, take a look. The size was cut in half. Do you see that? So we went from about 200 to 100. Look at this one. The size was cut in about, even though we took 2 electrons off magnesium, we're going to take 2 electrons off. What happened to the size? It was cut in about half, or a little more than the half. Take a look at what happens to the size here. Lithium to lithium ion. So 60, 152, that's close enough to being cut in half, roughly. That's very crude. Beryllium. Actually, beryllium's quite a bit different. Beryllium went from 111 to 27. That got cut a lot. In fact, beryllium. Another guy who's trying to I don't think they're trying to kill me, but I have a friend that works at JPL, and he buys surplus equipment that he keeps in his garage, but his garage is getting too full, so he asked me, can I hold some vacuum equipment for him? And the vacuum equipment's like this submarine-looking stuff, and so I said, oh, maybe. And then I was asking him about the vacuum equipment, and some of it had windows, and the windows were made out of beryllium. And so beryllium windows. Why beryllium? Because beryllium doesn't absorb much light. Beryllium doesn't have many electrons, and it's used for X-ray windows. So it passes X-rays quite nicely. Whereas lead, lead has a lot of electrons, and let's use as a lead X-ray absorber. Beryllium would be the opposite, an X-ray window. And so, I know of beryllium because there's a lot of aerospace here, and a lot of people were using beryllium metal for aerospace, but all those people who were machining beryllium metal ended up dying from beryllium poisoning. Beryllium is extremely toxic. And so, if somebody asks you, well, why don't you use, we could use calcium instead of barium, but you wouldn't want to use beryllium, because beryllium will lead to, I think very, very high death rate, but the thing is, it's not like acute. It doesn't happen quickly. It happens over time. And so everybody who was working with beryllium ended up dying from, I forgot exactly which disease, but so you don't hear about it that much anymore. But anyway, he was trying to get me to store beryllium windows in the garage. Didn't do that either. See, this is why I think, some people don't really care so much about it. Although it's probably safe, as long as nothing happens. All right. So what we say is this: as a crude measure, the ions are about half the size of their parent, the cations. You see these cations? Even like something like iron. If we go to iron, it's 124 to 77, so that's about half. But when we go to iron 3, it just goes down to 65, and so it's still about half. A little smaller than half. And so the cations are about half, and the nonmetals are going to form the cations. Also, the semimetals will form the cations. Now let's take a look at what happens with the anions. When you look at the anions, what happened when we add an extra electron to it? They get bigger. How much bigger? About double. And so the cations shrink by half. The anions double in size. And so what happens is this. The biggest atoms are at the bottom left. Where are the biggest ions? The biggest ions are at the bottom right. The biggest ions at the bottom right. The smallest ions are at the top left. So let's take a look at some of the biggest ions. Down here. Actually, we don't have too many more. Just, telluride and iodide are pretty big. At 220. Okay, let's look for the biggest cation. What's the biggest cation that you see? The biggest cations here, rubidium, 149. And then let's look for the smallest anion. The smallest anion is 133. And so this is not perfect, but we can come up with a generalization with a few exceptions. The generalization, this wouldn't be a law. The generalization is that anions are bigger than cations. Anions are bigger than cations. Because of this. With a few exceptions, fluoride, oxide, or the cations down there. All right, so even though like something like phosphorus gains 3 electrons, take a look at what happened to the size. The size just pretty much doubled. Whereas, chloride gained 1 electron and the size pretty much doubled. All right, that's the radius of atoms and ions. The next thing we're going to look at are ionization energies. Ionization energies are defined like this. We take a gaseous atom and knock an electron off. When magnesium reacts, 1 electron gets taken at a time. And so when magnesium reacts, we first form magnesium plus. Well, that can lose another electron, so magnesium plus will form magnesium 2 plus. But we separate these steps. The first step is I1, called ionization 1. It's going to cost you a lot of energy. Even though magnesium is a metal. Metals are electron rich, right? Well, what exactly do I mean by electron rich? Because magnesium burns very nicely, and that means it loses electrons easily. Well, this is what I mean by easily. To lose an electron is always going to cost you energy, 738 kilojoules per mole. In fact, to form magnesium 2 plus, you have to add these according to Hess's law. And so this is about 15, that's 17, so this is going to be about 2,200 kilojoules per mole to form magnesium 2 plus from magnesium. And so why the heck, 2,200 kilojoules is a lot. That would take UV light to knock an electron off magnesium, not visible. And so why the heck would magnesium react? Well, the reason magnesium reacts is, even though this is unfavorable, because this is not exothermic, this is endothermic, this is going to cost a lot of energy. The reason why magnesium reacts is because bonds are formed, and bonds are what we're going to talk about in the next chapter. Because we don't just can the magnesium ions. Magnesium ions by themselves are terribly unstable, right? And so we need a counter ion to bond to it. Now, these are a chart of I1s, and if you look at the ionization 1, just knocking 1 electron off these, you see a periodic pattern. The periodic pattern, hydrogen to helium. So as we go left to right in the periodic table, lithium to neon. Left to right in the periodic table, what happens? The ionization energy increases. And so that's what we'll see. I forgot to say one thing. Do you notice, before I get to ionization, do you notice something with the size here? 125, 124, 124, 125, 125. Transition metals are flat. Here, do you see that? The size is not shrinking. And so what I forgot to mention is this. For the transition metals, what you see here is that we're increasing Z, but we're adding a same shell, actually 3D. Is it the 3D in the same shell as the 4s and the 4p? No, we call it an inner shell electron. And so when we add, we're adding an inner shell electron. Inner shell electrons are effective shielders. They can block the outer shell electron from seeing the full nuclear charge. And so what happens here is that, yes, we're increasing Z, but Z effective is not changing because each time in the D block we add a proton, we add an inner shell electron. And so these are effective shielders. The same thing happens in the lanthanides and the actinides. And they call them lanthanides, they call it the lanthanide contraction. The lanthanides are the F block, cerium to lutetium. Yes.
So, what about a shell electron?
Same shell electrons are not effective shielders. This is the whole shielding business we were talking about earlier, just with multicolored graphs. This is Z effective, some numbers for Z effective you can look up. I gave you a homework problem using Slater's rule to estimate Z effective. But you can see the shielding differences. If 1s is shielding all these others. And we can see which ones are most penetrating. This is the RDF, radial distribution function. But when we add an inner shell electron, this is what happens. This is the flattening out here. Because here we're adding a proton, adding a same shell electron. Add a proton, but when we hit the D's, we add a proton, we're adding an inner shell electron, and then it flattens. You can see here, and here. Here for the, this would be for the, so 1, 2, 3, actually no, this is, there's some weird stuff going on as well. We'll look at that. Okay, we want to look at some of the weird stuff that's going on this chart. Because basically, ionization energy pattern is very simple. The ionization energy, I1, right, increases with decreasing radius. And so the smaller the atom, the harder it is to ionize. So helium's the smallest. This is going to be the hardest to ionize. It makes sense because it's going to have the highest Z effective. And so this is going to be the hardest to ionize at about almost 2,500 kilojoules per mole to ionize. Hydrogen's ionization energy was about 1,300 kilojoules per mole. Helium's is much higher. Lithium is bigger than beryllium. So beryllium's smaller, beryllium's harder to ionize. And so this point here is for beryllium. Beryllium's smaller. But this point here is for boron. Boron's smaller. Boron's smaller than beryllium. Why is it easier to ionize? And so this is an exception. Boron is smaller, but easier to ionize. And so we have to come up with some kind of understanding of why that is. Because I just said this, that the smaller the radius, the higher the ionization energy. And so the situation is now we have to look at what electron are we ionizing. In beryllium, we're ionizing one of the 2s electrons. In boron, we're not ionizing a 2s electron, we're ionizing a 2p electron. And so even though boron is smaller, the reason why it's easier to ionize is because 2p's are less penetrating. 2p's less penetrating, easier to ionize. Okay, then when we go from boron, we'll hit carbon here. Well, carbon's smaller than boron, and it's a 2p. And so now it goes back to what we expect. But when we go to from carbon to nitrogen, that's fine. Nitrogen is smaller here. But when we go to oxygen, again, what's oxygen versus nitrogen? Oxygen is smaller than nitrogen. Why is oxygen easier to ionize than nitrogen? Why is oxygen easier to ionize than nitrogen? Well, we have to take a look at what electrons being taken. And so if we try to ionize nitrogen, nitrogen is like this. It's a 2s and then 2p3. And so when we try to ionize nitrogen, we take one of the 2p electrons out of there. Versus oxygen. When we oxidize oxygen, we're also taking a 2p electron. which 2p electron do you think will be removed? We're going to take this one here. And so the reason why oxygen is easier to ionize than nitrogen is because we're removing a paired electron versus an unpaired electron. A paired electron is going to have something called electron-electron repulsions, because when you put two electrons in an orbital, they're both negatively charged. And so there's going to be some electrical repulsion, which helps the ionization process, which makes it easier to ionize. And so nitrogen and oxygen is, and so the exceptions are, this first exception is a P versus S. The second exception here is unpaired versus paired. And we see this pattern repeat. For example, here with aluminum, do you see the drop for aluminum? This is due to a P in aluminum being ionized versus an S here in what would this be, magnesium? Okay, so magnesium versus aluminum. Well, aluminum, because it's a P on magnesium versus an S, on aluminum, the P on aluminum versus an S on magnesium. And then do you see this blip here? That blip is for phosphorus and sulfur. Here, phosphorus and sulfur. Sulfur is going to be easier to ionize because we're taking a paired versus an unpaired. Now, as the atoms get bigger, this becomes less pronounced here. And so it's the biggest will be for the smallest atoms here. As the atoms get bigger, then electron-electron repulsions aren't that big of a deal. And they're both not very penetrating, those high-end S&P orbitals. And so this is ionization energy 1. We're going to look at subsequent ionization energies. What's the highest ionization energy for I1? It's about 2,500 kilojoules per mole. The lowest for I1. The lowest is going to be about cesium at 375 kilojoules per mole. And so it ranges from a few hundred to thousands of kilojoules per mole, the ionization energy ones. But we can see, based on size, cesium is going to be easy to ionize because it's so big. This is a very low ionization energy, and it makes cesium highly reactive. You know, cesium is a very powerful reducer. Lithium has a higher ionization energy, a much higher ionization energy because it's a much smaller atom. But we have a conflict here. What's the strongest reducer on the chart? The strongest reducer on the chart is on the redox chart. Lithium. Lithium is the strongest reducer, meaning that it's the most electron rich. But when we look at the data, it doesn't match. There's a conflict here. Because lithium is the strongest reducer, and then sodium is a weaker reducer, but it's easier to pluck an electron off sodium. It only costs you 500 versus lithium, which costs you 520. And so, what's going on there? What's going on there is we aren't looking at the whole picture. Ionization is just part of a redox reaction. The other part is what we form. And so lithium forms quite stable ionic compounds because of its small size. You can form strong ionic bonds. But it's not as reactive. You know, lithium costs you a lot more energy to react, so sodium reacts much more violently. So for example, if you put lithium in water, it just bubbles slowly. If you put sodium in water, it catches on fire. Potassium in water, it explodes. Cesium in air, explosive. You know, cesium is, you never want to expose this to air because you'll have a very violent reaction because its ionization energy is so small. And so there's a difference. When we look at the redox chart is looking not just at reactivity, but at the final product too, which is lithium ions in water, which are quite stable. But lithium isn't as reactive as some of these. You know, these other ones react much more violently, but they don't form as stable products. That's the only difference. All right, the next thing we're going to look at are, well, actually, let's not look at the next thing. Let's look at the first thing. Sodium versus argon. Which one's bigger, sodium or argon? No. Which one's bigger, sodium or argon? Argon. Why is argon smaller? Or did I ask you which one's bigger? Oh, sodium's bigger, sorry. Sodium's bigger. Argon's smaller. Why is argon smaller? Yeah, Z effective. Z effective increases same shell electron. And so the size decreases this way. And therefore, the ionization energy should increase this way. Except we see an exception here. Take a look. Increase, and then magnesium to aluminum actually drops. Why? S versus P. Easier to ionize a P. Then increases, and then from phosphorus to sulfur, it drops. Why? Paired versus unpaired. Paired in sulfur, unpaired, and so easier to ionize a paired electron. And then it increases this way. And so we see this pattern for the I1s. Now we're going to look at successive ionization energies, I2, I3. We're going to just try to take off more electrons and then see. And so if you wanted to form a sodium plus 2 ion, how much energy would it cost? Well, to form a sodium plus 1 is going to cost you 500. To form a sodium plus 2 is going to cost you 500 plus 4,500. So altogether, to form a sodium plus 2 is going to cost you 5,000 kilojoules per mole. Is that a lot of energy? That's a lot of energy. That's a lot of energy, so sodium plus 2 doesn't form. So what we say is that the ionization energies for the core electrons are very high. Take a look at what happens. It went up about 10-fold. And so it costs you about 10 times more energy to ionize a core electron than a valence electron. Why? Because you got to, destroy that symmetry of the core, the filled shell. Let's look at magnesium. Ionize the first electron, 700. Ionize the second electron, 1,400. And so the second ionization energy doubled. But if we try to ionize the third electron, what happened? About 10-fold increase. This is really crude, 10 plus or minus a bunch, but still, it's about 10 times more energy to ionize a core. And the same thing, aluminum. First electron, second electron doubled or more than doubled. Third electron, more than tripled here. But to take the fourth electron, and so anyway, we have this boundary here. The core electrons, take a look at how much energy it costs to ionize a core versus a valence electron. And so if we look at valence, chlorine plus 1, chlorine plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. We'd have to add all these up. And still, chlorine in the plus 7 oxidation state isn't like removing a core. But it's a tremendous amount of energy here. Argon has a very high ionization energy, extremely high, 1500. That ionization energy on argon means argon's very unreactive. But then you go 1500, that's like this. Well, it also has to do with the stability of what you can form afterwards. And so that's something about the successive ionization energies here. Let me go on to electron affinities. Electron affinities are the opposite. Here we take a gaseous atom and add an electron. So this is called EA1 or delta HEA. The electron affinity here is, usually electron affinities are exothermic here, except for the noble gases and group 2. They're exothermic. And so they form something more stable. Obviously fluorine wants an electron, right? What's the strongest oxidizer? Fluorine's the strongest oxidizer. And so when fluorine gains an electron, releases 328 kilojoules per mole in the gaseous state. But there's something funny in the numbers, something that doesn't match. Fluorine should be the most exothermic because fluoride should be more stable than fluorine. But look at chlorine. Chlorine has a higher electron affinity. That is, it releases more energy. And so fluorine's 328, chlorine's 349. What's going on there? Oxygen is only 141. And so why would chlorine have a higher electron affinity? Electron affinity is liking for electrons, right? Well, electron affinity deals with two things. And so there's one exception here. Fluorine for sure is going to be the most reactive. You know, it's the smallest, the highest is the effective out of the halogens. And so this is more reactive, but chlorine has a higher electron affinity. Because electron affinity is a composite of two things. EA, electron affinity, is the electronegativity plus the ability to hold the electron. And so what has the highest electronegativity? Fluorine. But fluorine's 2p orbital, when that goes in, that electron goes in, it goes into a 2p orbital on fluorine. And so if we look at a 2p orbital on fluorine, it's small. 2p. 2p can hold 2 electrons, so an extra electron goes in there. It gets a little bit crowded. Whereas chlorine is 3p orbital. This is 2p. Chlorine has a 3p orbital. It can much easier accommodate that because there's less electron-electron repulsions. The greater electron-electron repulsions here. In fluorine than in chlorine. And so yes, chlorine has a higher electron affinity, but fluorine's still going to be the most powerful oxidizer. We don't worry about this too much. We just use the numbers to do calculations. That's all. Delta H's we use in Hess's law. And so we need these delta H values. But you can see the noble gases don't want another electron, so these are highly endothermic. They're going to produce something unstable. And also the group 2. The group 2 as well, you know, they don't want, because that's going into the next subshell. And so here, you know, these would be going into the next subshell. And so beryllium, nah, it's not going into the 2s, it's going into the 2p, which is going to be less favorable. But as the orbitals get bigger, then it's not a big deal. But small orbitals, it's more significant. All right, there's EA1 and there's EA2. EA1 is exothermic, EA2 is typically endothermic. And so if we look at oxygen, adding the first electron is favorable. minus 141. Adding the second electron is highly unfavorable, plus 744. And so net, to form O2 minus from O, is going to be a net endothermic process. It's going to cost you about plus 600 kilojoules per mole. 600 kilojoules per mole is a significant quantity of energy. And so we have something that's very strange here. Okay, in order to go, we know magnesium and oxygen react. This forms magnesium oxide solid, right? This is a very favorable reaction. This is highly exothermic. And so in Chem 4 you learn, why does magnesium form magnesium 2+? Well, it's got the stable noble gas electron configuration, but is it really stable? No, because it's going to cost you 2,000 kilojoules per mole. So going from magnesium in the gaseous state to magnesium 2+ in the gaseous state costs you about 2,000 kilojoules per mole. 2,000 kilojoules. Going from oxygen in the gaseous state to oxide in the gaseous state is going to cost you about 600 kilojoules. So altogether, we're looking at 2,600 kilojoules worth of energy to form the noble gas electron configuration ions. And so why even bother forming the ions if it's going to cost you 3,000 kilojoules? Why would you? Why would you even bother forming the ions? The reason the ions form is because of the bonds. When we form an ionic lattice like that, we are going to release a lot of energy. And so this is very costly, but a big return when bonds are formed. And so this is like an initial investment. You have to invest a lot of money initially, but you're going to get a big return in the end. The big return is going to come from forming an ionic bond. An ionic bond is Mg2+ and oxide 2-, right? This ionic bond actually, not just one ionic bond, but a lattice of ionic bonds, right? We're going to have a lattice of ionic bonds. Lattice of ionic bonds. And so what nature does is it looks at the cost versus the benefit. What would make a stronger ionic bond? A magnesium +3 or magnesium +2? What would make a stronger ionic bond? Magnesium +3 or magnesium +2? Magnesium +3. You'd get a much stronger bond if we use magnesium 3+ versus magnesium 2+. A much stronger ionic bond. If we had magnesium 3+ with an oxygen 3-, that would make an incredibly strong bond. But it doesn't happen. Do you know why it doesn't happen? It doesn't happen because forming magnesium 3+ costs way too much energy. And so the reason why valence electrons react is those have reasonable cost, and then the benefit is good because you can form strong bonds. Versus if you start digging into the core electrons, the cost becomes too great, even though the bonds and the payoff would be better. Okay.